Okay, I have written the earlier results here. Okay, we have got two linear equations and we have rewritten in terms of these equations in terms of a matrix equation. So we have seen that in the degenerate theory, essentially what we have to do is solve this eigenvalue equation. Now let us try to find out the eigenvalues of these equations. Okay. Let me say eigenvalues of equation 10. How do we solve this equation? By the eigenvalue procedure, we have to find the roots of the characteristic equation, right? So what are the roots? What is the characteristic equation? H prime minus some lambda identity. This is the characteristic equation where lambda are the eigenvalues. Okay, so this is the H prime matrix. So what is H prime and determinant of H prime minus lambda I? It will be H prime. The diagonal elements will have this minus lambda term. So H prime AA minus lambda. This will be H prime AB. H prime BA. Here you have H prime BB minus lambda. If we take this difference, determinant is equal to 0. Let us evaluate this determinant. So we have H prime AA minus lambda, H prime BB minus lambda minus these two terms. But we can say H prime BA is actually the complex conjugate of H prime AB. For example, what is H prime BB? Psi A0, H prime psi B0. This is H prime AB. Right? What is H prime BA? Is psi B0, H prime psi A0. This is H prime BA. Now, if you look at the left hand side, this is actually the change of bra vector and interchange of bra vector and ket vector in this matrix element. So, when you interchange the bra vector and ket vector in an inner product, you get a complex conjugate. So, what you have is H prime BA. You can write as H prime AB star. Okay. So if we use that, then this is actually modulus H prime AB square is equal to 0. Let us expand this. Okay. So if you expand this one, what you have is, I will first write the lambda square term. So minus lambda into minus lambda, you have a lambda square minus lambda times H prime AA plus H prime BB, then plus H prime AA, H prime BB, okay, product of these two. This is the expansion of this two brackets, and there is this term also, minus H prime AB square equal to 0. Now this is a quadratic equation in lambda. So we can, what are the solutions? Solutions are lambda equals, this is from the form a lambda square plus b lambda plus c equal to 0. So we know the solutions of quadratic equation, minus b plus or minus root of b square minus 4ac by 2a. So what is a here? 1. So in the denominator we have only a 2. So I can put it as 1 by 2, right? Minus b, this is the b term with a minus sign. So what is minus of b? This one. So we have H prime AA plus H prime BB minus b plus or minus square root of b square, that is the square of this one, H prime AA plus H prime BB. Actually this is minus b, but when you take the square, it's not important. So whether it is minus or plus, so minus b square will be this one, b square minus 4ac. A is 1, this is c. So 4 times H prime AA H prime BB minus modulus H prime AB square. We get this. Okay. All divided by 2a, that is 2. We can make a simplification here. So we can see that there are two terms for lambda. Lambda can be this plus this one or this minus this one. Okay. Now these two terms, let me write as e plus 1 and e minus 1. This plus sign stands for putting plus here, minus sign stands for putting minus here. Okay, that is the justification of our earlier notation. And why do I put superscript 1? Because what we ultimately get is first order correction in energy. So what are the two values? E, instead of lambda, let me write e plus or minus 1 is equal to half H prime AA plus H prime BB plus or minus. Okay, we no longer need this part. Plus or minus square root of, see, if we expand this part, we have a minus 4 times H prime AA, H prime BB plus 4 times H prime AB square. Look at this minus term. If you expand this part, what you get? H prime AA square, H prime BB square plus 2 times H prime AA, H prime BB. You have a minus 4 times H prime AA, H prime BB here. So if this plus 2 and minus 4 will cancel, you get a minus 2 term. So this is an a plus b whole square term, this is a minus 4ab term. If you subtract that, what you get is a minus b whole square. So what you have here is H prime AA minus H prime BB square. Okay. So a plus b whole square minus 4ab we have written as a minus b whole square, and what is remaining? Plus 4 times H prime AB square. Right. So these are the energy eigenvalues that we have obtained. Okay. Corresponding to this plus symbol we have got 1, and corresponding to this minus symbol we have got the other. Okay. Now let us ask the question, what happens if our original eigenstates, okay, we started with the degenerate eigenstates psi a0 and psi b0, and finally what we have done is after solving the eigenvalue equation, we got two sets of values for alpha and beta. Then we took a linear combination of psi a0 and psi b0, and finally what we have done is corresponding to the two sets of values for alpha and beta, we have got two good choices of the linear combination of psi a0 and psi b0, which we called psi plus 0 and psi minus 0. Okay. Now let us say what happens, let us ask the question, what happens if our original choices, psi a0 and psi b0, original degenerate eigenstates, what if they were the good eigenstates? Okay, what happens if they are the good eigenstates? Okay, let us see. So this is our question. What happens if psi a0 and psi b0 are the good eigenstates? The good means that in this basis the perturbing Hamiltonian will be diagonal, and the diagonal elements will be the first order correction in energy. You know that when an operator matrix is diagonal, the diagonal elements are the eigenvalues. Okay. So what happens if psi A0 and psi B0 are the good eigenstates? Let's see. So psi okay, so suppose psi A0 is a good eigenstate, okay? Then so first we can say psi A0 is a good eigenstate, which means that our psi 0, okay, we have chosen as the unperturbed state some psi 0. What was psi 0? Linear combination of psi A0 and psi B0. What was the expression for psi 0? Alpha psi A0 plus beta psi B0. So if psi A0 is a good eigenstate, one choice of psi 0, another way of putting it is, one choice of psi 0 is nothing but psi A0. Psi, okay? If this is a good eigenstate, then psi 0 is simply psi A0. Instead of choosing a linear combination, we can simply choose psi A0. So what does it mean is that alpha is equal to 1 and beta is equal to 0. Because psi A0 we have written as alpha psi A0 plus beta psi B0. So the choice of psi 0 equal to psi A0 means that our coefficients alpha and beta, they can have any values. These should be the values of alpha and beta. So what we are doing is, we are considering a particular choice of psi 0 with these coefficients. Let us see what happens. Now when alpha equal to 1 and beta equal to 0, I have removed it. We have some two linear equations in terms of alpha and beta. Let's see what are they. They are alpha times h prime AA plus beta times h prime AB equal to alpha times E1. I think some equation 7 or 8. Then next one was alpha times h prime BA plus beta times h prime BB equals beta times E1. These were our linear equations. We have written them as in matrix form. Now if alpha equal to 1 and beta equal to 0, I think this was equation 8 and this was equation 9. Okay. Look at equation 8. Alpha equal to 1, okay, beta equal to 0. First let us look at let us look at equation 8. Alpha equal to 1 and beta equal to 0. So when beta equal to 0, this term is gone. When alpha equal to 1, what you get is equation 8 gives E1 equal to h prime AA, correct? Beta equal to 0, alpha equal to 1, so E1 is equal to h prime AA. The first order correction in energy is h prime AA. What is h prime AA? First diagonal element of the perturbing Hamiltonian, matrix of the perturbing Hamiltonian. What about equation 9? Equation 9 gives alpha equal to 1 and beta equal to 0, right? Beta equal to 0, this term is gone. So this is 0, this is 0. Alpha equal to 1. So what you get is h prime BA equal to 0. Okay. So h prime BA equal to 0. We know that h prime AB is the complex conjugate of h prime BA. So which means that h prime AB is also 0. So what you see here is the off-diagonal elements of the Hamiltonian will be perturbing Hamiltonian matrix will be 0, and the first diagonal element is nothing but the first order correction energy E1. Okay, that's what we get. Let us look at the second choice. Psi B0 is the good eigenstate, right? So if psi B0 is a good eigenstate, then psi 0 is nothing but psi B0. This is the second choice, right? Psi 0 is equal to psi B0. Now if this is the case, then alpha is equal to 0 and beta equal to 1. Okay, this is another choice for psi 0. Instead of taking the linear we are taking the linear combination with this alpha and this beta. So psi 0 contains only psi b 0. Let us look at equation 8 and 9. What happens when alpha equal to 0 and beta equal to 1? Okay, alpha equal to 0 and beta equal to 1. So alpha equal to 0, these two terms become 0. Beta equal to 1. So h prime ab equal to 0. So equation 8 gives h prime ab equal to 0. Which also means that h prime ba is equal to 0. Because h prime ba is the complex conjugate of h prime ab. And what about this one? Equation 9. Alpha equal to 0. This term is gone. Beta equal to 1. So what you get is E1 is equal to h prime bb. So again, off diagonal elements of the perturbing Hamiltonian matrix is 0, and the second diagonal element h prime bb is nothing but the first order correction in energy, right? But are they same? Are these two first order correction energies? So what we essentially have is if we choose psi a0 and psi b0 as the correct eigenstates, as the good eigenstate, as the correct basis, okay, then what we see is that the perturbing Hamiltonian, the off diagonal elements of the perturbing Hamiltonian will go, and the diagonal elements are the first order correction energy. But are they equal? Okay. In order to find out that, let us look at this equation. Okay. So let us look at this equation and see what happens. So what we have seen is that when we make this choice, either alpha equal to 1 and beta equal to 0, that means either psi 0 equal to psi a0, or alpha equal to 0, beta equal to 1, that is psi 0 equal to psi b0. In both cases, this h prime ab will be 0, off diagonal elements will be 0. Now if these off diagonal elements will be 0, let us see what happens to our energy eigenvalues. E plus minus 1 is equal to half into this term h prime aa plus h prime bb plus or minus. So if this is gone, then we have square root of a perfect square. Okay, its square root can be either h prime aa minus h prime bb or h prime bb minus h prime aa. So let us assume that h prime aa is greater than h prime bb. Okay, so the positive root is we have h prime aa minus h prime bb. Here assume that h prime aa is greater than h prime b. So we have simply taken the positive root. This is our expression. So we have two choices. If plus sign is written, then what is e plus 1? This is equal to, if suppose the plus sign is here, then we have, if there is only plus sign here, right, then this h prime bb and minus h prime bb will cancel. H prime aa plus h prime aa will be 2 times h prime aa, that 2 will cancel here. So e plus 1 will be h prime aa. On the other hand, if you put the minus sign here, okay, suppose there is a minus sign here, then h prime aa and minus h prime aa will cancel. This will be minus of minus plus. You have 2 h prime bb, 2 will cancel. So we have h prime bb. So the first diagonal element of the Hamiltonian, perturbing Hamiltonian matrix will be E plus 1. Okay, one correction in the energy. Second diagonal will be E minus 1. So it means that in this basis, in the basis of psi a0 and psi b0, if these are the correct basis, our perturbing Hamiltonian will look like this. The first diagonal element will be E plus 1, the diagonal element will be E minus 1, and the off diagonal elements h prime ab and h prime ba will be 0. Okay, this is what I have stated earlier. If we have a set of good eigenstates, okay, in this case our good eigenstates are psi a0 and psi b0, then the perturbing Hamiltonian will be diagonal in that eigenstate, in the good eigenstates, and the diagonal elements are nothing but the first order correction in energy. We will see this case when we work out a particular example. So solving the degenerate perturbation theory is equivalent to solving an eigenvalue equation for the perturbing Hamiltonian. In another way is we can say that it is equivalent to diagonalizing the perturbing Hamiltonian in the degenerate subspace. Okay, we have diagonalized the perturbing Hamiltonian only in the degenerate subspace. Then the problem of the denominator vanishing can be removed. How it can be removed is if you remember the expression for the first order correction in wave function and the second order correction energy, what happens in the degenerate subspace is the numerator term. Actually, the numerator term, if you remember, these are off diagonal matrix elements. The numerator term in the expression for first order correction energy gets psi 1, and the second order correction first order correction wave function gets psi n1, and the second order correction energy en2. Numerator term will be something like psi m0 h prime psi n0, but with m not equal to n. Okay, these are off diagonal elements of the matrix of h prime. Now we see that when you diagonalize the perturbing Hamiltonian in the degenerate subspace, the off diagonal elements are 0. Numerator goes to 0. Okay, so that problem of vanishing denominator is not there. Okay, because numerator also has gone to 0. So once we diagonalize the perturbing Hamiltonian in the degenerate subspace, we have got the first order correction energy. Okay, and that the problem with the terms denominator vanishing issue can also be solved. What is the value of this first order correction energy? Look at this. E plus 1 is h prime A. What is this h prime A? If we expand this is psi A0 h prime psi A0. And what is h prime BB? Psi B0 h prime psi B0. Look at these expressions. These are the expectation value of h prime in the unperturbed state. Expectation value of h prime in the unperturbed state. Okay, in one unperturbed state and the other unperturbed state. So this is exactly like the first order correction in energy in the case of non-degenerate case. Okay, so what we have to do in degenerate case is you find out the correct or good eigenstates to diagonalize the Hamiltonian. Then you just apply first order correction. That means you just treat it as non-degenerate case. Okay, you can just calculate the first order correction energy once you have the correct eigenstates, then you just calculate the first order correction energy as the expectation value of the perturbing Hamiltonian in these eigenstates. That's all. Now in this context, so this is the solution of the degenerate theory. In this context, we can ask the question, is there any easy way to identify these good eigenstates? So what we have seen repeatedly is that the degenerate theory amounts to identifying the good eigenstates of the perturbing Hamiltonian. So if we can start with, if we already know the good eigenstates, then we can just find the matrix element of the perturbing Hamiltonian in that good eigenstates. Automatically perturbing Hamiltonian will be diagonal in that good eigenstates, and the diagonal elements will be the first order correction energy. Okay, if we don't know what are the good eigenstates, then we have to solve the eigenvalue equation. We have written some equation 10. That eigenvalue equation we have to solve. Then we will get two values for energy. We will get an expression like this, two values for energy, and the corresponding eigenstates will be two sets of values for alpha and beta, which gives you the correct linear combinations of the old eigenstates, which were not good. Okay. So we can, I ask, is there any good way, is there any easy way to identify these good eigenstates? Actually, there is an easy way. Let us see what it is. Let us ask this question. Is there an easy way to identify the good degenerate eigenstates of H0? Because to start with, if we already know the good degenerate eigenstates of H0, the problem is very easy. You need just to write down the the matrix of the perturbing Hamiltonian in those eigenstates. That will be diagonal, and the diagonal elements will be the first order correction energy. Okay, so this is the crucial question. Actually, it turns out that there is an easy way. There is a theorem which states that if there is a Hermitian operator, okay, if there is a, let me write in mathematical terms. Suppose there is a Hermitian operator, okay, let us say some operator A, which is commuting with both the unperturbed Hamiltonian and the perturbing Hamiltonian. Okay, so if there is a Hermitian operator A which is commuting with both the unperturbed Hamiltonian and the perturbing Hamiltonian, suppose there is such a Hermitian operator, and if the degenerate eigenstates of unperturbed Hamiltonian are non-degenerate eigenstates of this operator, okay, then so it is clear that if these A and H0 are commuting, then they have common eigenstates. So consider the degenerate eigenstates of H0, let us say some twofold degenerate eigenstates of H0. Then they will be eigenstates of A also. But these are degenerate eigenstates of H0, but they are non-degenerate eigenstates of A, corresponding to two different eigenvalues. Then those degenerate eigenstates of H0 will be the good eigenstates for our problem. Okay, let me restate the theorem. Suppose there is a Hermitian operator which is commuting with both unperturbed Hamiltonian as well as perturbing Hamiltonian, right? And if the degenerate eigenstates of H0, okay, here is the confusion, which degenerate eigenstate we have to choose as the correct eigenstates. So if the degenerate eigenstates of H0 are non-degenerate eigenstates of A, then those degenerate eigenstates of H0 are a good set of eigenstates to build the perturbation theorem, to diagonalize the perturbing Hamiltonian. Okay, let us try to prove this. So these are commuting. A is commuting with both H0 and H prime, and next is suppose this psi A0, let us use our earlier notation. Psi A0 and psi B0 are degenerate eigenstates of H0, twofold degenerate eigenstates of H0. But so they are also eigenstates of A, but they are non-degenerate eigenstates of A. Suppose when A acts on psi 0, we get some mu times psi 0, psi A0, and when A acts on psi B0, we get some mu times psi B0 with mu not equal to mu. So that means psi A0 and psi B0 are eigenstates of A with different eigenvalues. They are non-degenerate eigenstates of A. Then we have to prove that then psi A0 and psi B0, these degenerate eigenstates of H0, are a good choice for writing the matrix H prime. Okay, that's what we are going to show. Okay, so let us start like this. So we know these results. Now let's start with this equation. A acting on H prime is equal to 0. I mean, not A acting on H prime. The commutator between commutator between A and H prime, perturbing Hamiltonian, is 0. So that means if you take the matrix element of this commutator, it will be 0. Let us take the matrix element like this: between psi A0 and psi B0. Okay, so if this commutator is 0, any matrix element of this commutator will be 0. Commutator is an operator. Let us expand this. We can remove this part. So if you expand the left hand side, psi a0. This expansion is ah prime minus h prime a. So there are two terms. First term will be ah prime. Ah prime psi b0 minus next term will be h prime a. So psi a0 h prime a psi b0 is equal to 0. Now here a is a Hermitian operator, h prime is also a Hermitian operator. Now a can act on this one, can act on this bra vector psi a0. Okay, what is happening when a acts on psi a0? Earlier we have written a acting on psi a0, we get some mu times psi a0. Psi a0. A being a Hermitian operator, mu, the eigenvalue must be real. So you can take this mu outside from the bra vector. Since it is real, there is no change in there is no complex conjugation. So what you get is mu times psi a0 h prime psi b0. Here a can act on the right side, ket vector. Okay, a acting on psi b0 will give some mu times psi b0. Okay, so you have mu times psi b0. Nu is a scalar, real scalar. We can take it outside. So nu times psi a0 h prime psi b0 equal to 0. Right? Now these two terms are same. These matrix elements are the same, so we can take it as common. So we have mu minus mu psi a0 h prime psi b0 equal to 0. Okay. Now we know that mu and nu are different because psi a0 and psi b0 are non-degenerate eigenstates of A. So these eigenvalues are different. So mu is not equal to nu, which implies, so if this product is 0, either mu minus nu should be 0 or this matrix element should be 0. If mu and nu are different, this mu minus nu is non-zero. So this matrix element should be 0. That is psi a0 h prime psi b0 should be 0. But what is this matrix element? This is nothing but h prime ab. This is nothing but the off diagonal matrix element of h prime in the basis of psi a0 and psi b0. So off diagonal matrix elements are 0. Off diagonal matrix elements are 0 means this is a two-fold degeneracy. So it's a two-dimensional degenerate subspace. So matrix of h prime must be 2 by 2. So if the off diagonal matrix elements are 0, h prime ab 0 means h prime ba is also 0 because it's only a complex conjugate. So if the off diagonal matrix elements are 0, which it means that h prime matrix must be diagonal in this basis. Okay, if a matrix is diagonal in a basis, the diagonal elements are eigenvalues. Okay, so it is clear that h prime, the perturbing Hamiltonian, is diagonal in this basis. It means that this basis, psi a0 and psi b0, which are degenerate eigenstates of h0, are the correct choice of eigenstates to write the to diagonalize the perturbing Hamiltonian. Okay, so what is the procedure? What we have proved here, this theorem, what we have proved here is that if there is a Hermitian operator, some Hermitian operator which is commuting with both the unperturbed Hamiltonian h0 and the perturbing Hamiltonian h prime, then and there is one more condition, then they have common eigenstates between h0 and A, right? So if you have a set of degenerate eigenstates of h0, where the problem is for perturbation theory, if we have a set of degenerate eigenstates of h0 which are non-degenerate eigenstates of this operator A, then it is proved that these degenerate eigenstates of h0 are the correct choice of diagonalizing h prime. If we choose these degenerate eigenstates, it is guaranteed that the perturbing Hamiltonian h prime will be diagonal in this basis, right? And the diagonal elements will be automatically, we can look at these diagonal elements and write down the first order corrections in energy. Okay, this idea becomes more clear when we look at specific examples, and we will now do this, completes our discussion on the theory of degenerate perturbation. theory part is over. So what are the end results? The end results is that when there is degeneracy, there is a problem in following the prescription of a non-degenerate theory, because the denominator of psi, the first order correction wave function, hence the second order correction energy becomes 0. So those terms will become infinitely large. So we need a new method. So what is this new method? This new method boils down to this. What we have to do is, you take the perturbing Hamiltonian and diagonalize it or find its eigenvalues in the degenerate subspace. Okay. So if the degeneracy is twofold, our perturbing Hamiltonian will be a 2 by 2 matrix in that degenerate subspace. We need to diagonalize it. That means we need to solve its eigenvalue equations. When you solve the eigenvalue equation or diagonalize it, the eigenvalues that we obtain for that particular eigenvalue equation in the degenerate subspace, the eigenvalues will be first order corrections in energy, and the eigenfunctions will give you the different choices of linear combinations in that degenerate subspace. In other words, different choices of correct eigenstates to be chosen as the basis of that degenerate subspace. Okay. So if we choose those eigenstates, that perturbing Hamiltonian will be diagonal. In other words, so the single point idea is that diagonalize the perturbing Hamiltonian in the degenerate subspace. That is the one line for degenerate theory. So diagonalizing a Hamiltonian in a degenerate subspace is equivalent to choosing the correct set of good eigenstates of the unperturbed Hamiltonian in which we can diagonalize it. If we make the correct choice, we don't have to solve the entire eigenvalue equation. You just have to write down the Hamiltonian, perturbing Hamiltonian in that correct eigenstates. Perturbing Hamiltonian will be diagonal, and the diagonal elements will give you the first order correction in energy. So then the question is, how do we choose is there any easy way to identify this correct set of degenerate eigenstates of the unperturbed Hamiltonian? Yes, there is a way. That is what we have shown that there is a theorem. You have to look around for some Hermitian operator that commutes with both H0, unperturbed Hamiltonian, and H prime, perturbing Hamiltonian. And the second condition is that the degenerate eigenstates of the unperturbed Hamiltonian must be non-degenerate eigenstates of this operator. Then it is guaranteed that if we start with those degenerate eigenstates of the perturbing Hamiltonian, of the unperturbed Hamiltonian, then our perturbing Hamiltonian will be automatically diagonal. Because this operator A commutes with, there is a connection, it commutes with H0 as well as H prime. So if these are non-degenerate eigenstates for A, then it is guaranteed that the H prime will be diagonal in that set of degenerate eigenstates of H0. So that is the correct way. So most of the time we are able to identify such an operator, okay, and then the eigenstates of that operator will be, they are non-degenerate eigenstates of that operator A. They are also degenerate eigenstates of the unperturbed Hamiltonian H0. Though the eigenstates of this operator A will be the correct set. That is the idea, correct choice of eigenstates. Okay, now what we have to do is we have to apply this idea in different problems. So we will discuss a few problems using degenerate perturbation theory. Thank you.